Okay, so our next speaker is Jackson Melchert. He's a fourth-year PhD student at Stanford, and he's advised by Priyanka Raina. His research is broadly focusing on agile hardware development, and specifically he's focusing on automating the hardware and compiler generation for CGRAs. So he's going to be presenting his work, APEX, a framework for automated processing element design space exploration using frequent subgraph analysis. So Jackson, the floor is yours.
Thanks. Yeah, hi everyone. Thanks for coming. I'll be presenting APEX, which is a framework for automated processing element design space exploration. This work has been done as a part of the Stanford Agile Hardware Center. So some introduction. Coarse-grained reconfigurable arrays, or CGRAs, are an interesting accelerator architecture for various workloads. If you're unfamiliar, this is what the overview of a CGRA looks like on the right. It's a tiled accelerator architecture. In this case, there are two different types of tiles, PEs, or processing elements, that do the compute within your application, and memory tiles, which store and buffer data. These tiles are connected by a reconfigurable interconnect. And this interconnect works at the word level rather than the bit level. So they are much more performant and more energy efficient than FPGAs. However, they're much more reconfigurable than application-specific hardware accelerators. In addition, they're not just one design point. CGRAs, depending on how specialized they are, can be higher performance or more reconfigurable. In particular, the architecture of the processing element has a direct and significant effect on the power, performance, and area of the accelerator. The design space of CGRA PEs is fairly complex and large. Right? Here on the right, I'm showing 3 different axes that we've identified. The first is the number and type of operations that you include within your PE. The second is how those operations are connected within your PE. And the third is the I/O, so how you connect your PE tiles to the interconnect and to other PEs. A naive exploration of this design space would lead to tons of candidate PEs that would be expensive to evaluate. So in this project, we present APEX, which stands for Automated PE Exploration, which aims to generate efficient PEs from the applications themselves. Right? It encompasses everything from application analysis to PE specification, to CGRA hardware generation, to compiler generation as well. This is a fully automated framework. The first main contribution of APEX is application-driven PE exploration. On this slide, I'm showing a flowchart of what this looks like. On the left, it starts with an application data flow graph. At the end, we should produce some sort of PE specification, in this case, a merged PE graph. I'll go through briefly what each of these steps looks like. So given an application data flow graph, the first step is to find commonly occurring computational patterns within our application. In this example, I'm showing a data flow graph of a convolution. Here it has 4 multiplies and 4 adds. You can send this data flow graph into what's called a frequent subgraph mining tool, and it will pick out the most common subgraphs of this application. In this example, I'm showing 3 different examples of frequent subgraphs, each with a frequency of 4. Some of these frequent subgraphs represent good choices for including as operations within your PEs. For example, subgraph 2 is a map. You would want to include that if you're going to accelerate convolution. Some of these frequent subgraphs represent worse choices, right? Subgraph 3 has multiply followed by 2 adds. And if you were to include this as an operation in your PE, you wouldn't be able to use it very many times to accelerate your application graph. In order to identify these subgraphs that have a lot of overlapping occurrences, we use a technique called maximal independent set analysis. Right? The goal here during this step is to find the number of non-overlapping occurrences of a specific subgraph within our application. For this example, I'm choosing subgraph 3 again, which has a frequency of 4 within our application. This middle graph, I've highlighted each of the occurrences of subgraph 3 within our application. Each occurrence is a different color. You can see that a lot of them overlap. They share a lot of nodes. So on the right, I've created a new node with each occurrence represented by a node, and overlapping occurrences have edges between them in this graph on the right. Right? So the blue and the yellow occurrences don't overlap, so they don't have an edge between them. We can find what's called the maximal independent set of this graph on the right which will give us specifically the size of this maximal independent set, will give us the number of non-overlapping occurrences of the subgraph within our application graph. This means that we can use 2 fully utilized PEs that implement this operation to accelerate our application. We can use this technique to pick out all of the interesting subgraphs within our application, eliminating those that have too many overlaps. From this step, we have an ordered list of frequent subgraphs, with the most interesting subgraphs at the beginning of the list. At this stage, we can start to think about how to actually generate a PE architecture from these graphs. The method we've chosen for doing that is called subgraph merging. Essentially, we're going to take a bunch of interesting subgraphs, merge them together to form a PE that should be good at accelerating all of them. The main components of this algorithm are shown at the bottom. Here we have 2 different subgraphs representing 2 different frequent operations. In this merging process, the first step is to generate all the potential mergings between each of the nodes and edges in subgraph 1 and 2. Then in the next step, each of these potential mergings gets a new node and an associated weight. This weight represents the hardware benefit of doing one of these mergings. For example, if you have 2 adders and you merge them together, you save the area of an adder. Compatible mergings, so mergings that can coexist at the same time, have an edge between them. We can find what's called the maximum weight click of this compatibility graph, essentially giving us the optimal, the lowest cost merging of these 2 subgraphs. From this, we can reconstruct a merged graph. So you can see here, depending on the select of this multiplexer, can either implement the operation described in subgraph 1 or the operation described in subgraph 2. So this whole process starts with an application data flow graph. You can have one application data flow graph or many. And throughout this whole application domain-driven PE architecture creation tool, we pick out the common computational patterns in subgraph mining. We eliminate those that are less interesting, worse choices using maximal independent set analysis, and merge many of them together to form this merged PE graph. So when you're doing this type of merging exploration, this automatic design space exploration, you're changing the architecture of your PE, and you're adding new reconfigurable paths, new multiplexers, and you're also changing how you configure the PE. You're changing the configuration space. And in order to map applications to a CGRA with these customized PEs, you need to be able to update your compiler. So here, I'm showing an example of a rewrite rule. In the red on the left is a subtract, it's a formally specified IR node, and on the right is a PE, which is also formally specified. A rewrite rule describes how to implement the subtract on this PE. So that includes things like how do you map the inputs of the subtract, the inputs of the PE, as well as what the configuration of the PE is. So here, we want the instruction of the PE to be an add. We want to invert A and send in a carry bit. And this rewrite rule describes how to do the subtract on this PE. Now, if we have automatically generated CGRAs, PEs, we want to do this in an automated way. And to do that, we leverage an automatic rewrite rule synthesis technique using SMT. Here we can construct a formal equation that says there exists some instruction that for all inputs that you send into the subtract and into the PE, the outputs are equivalent. If this equation is satisfiable, if there's some instruction inst that makes this true, we know that we have the configuration of this PE that implements the subtract. We can do this process for all the operations that we're interested in, from the simple operations to the complex operations. If we do this, we can adapt our compiler to whatever PE architecture we want. So we integrate the process that I talked about before that results in a PE merged graph with a PE hardware compiler generation toolchain. Here we leverage a domain-specific language called Peek that's specifically for describing processing elements. Peek includes a compiler that not only generates rewrite rules using the technique described in the last slide, but also the PE RTL. The rewrite rules can be included in an application mapping step that maps an application, which goes into a place and route tool that can produce a configuration bit stream. The PE RTL goes into a CGRA hardware generation tool that creates the hardware for the entire accelerator. Using both of these things, we can automatically generate not only the hardware, but a full compiler to run whatever application we want on our customized CGRA with specialized PEs. This allows for very easy evaluation of the different PEs that we've explored. So to conclude the talk, I'll go over some evaluation of APEX. In all of the experiments that we've done, we compare against a baseline PE, which represents a pretty typical CGRA PE. It includes one multiplier, one ALU, 2 registers for integer operands, and bit registers, and a lookup table for bitwise operations. So what APEX does is, for a suite of image processing applications that I've shown on this slide, it mines the most frequent subgraphs, the most frequent operations in those applications, and then eliminates those that have a lot of overlaps. Here, for each of these applications, we're generating a specialized PE for each of them. So there's one PE spec for camera pipeline, one PE spec for Harris, and so on. They include all of the operations shown in these boxes. These are fully specialized towards each of these applications. Additionally, if you're generating a CGRA, you might want something a little more general, more reconfigurable. So we also generate, APEX automatically generates a PEIP that's specialized across these applications to the image processing domain. The PEIP merges all of the operations that are shaded here in this grayish box. So in this slide, I'm showing some area and energy reports for full CGRAs that we've generated with these specialized PEs. So you can see there's 4 columns for each of the 4 image processing applications, and each bar is broken down into the component parts of the CGRA, with the PE specifically on the bottom in the dark blue. So you can see, going from the baseline PE to the PE that's specialized to image processing, we see significant decreases in both the area and the energy of the PE, which results in a decrease in the CGRA, full CGRA energy and area as well. Additionally, as you would expect, as we go from this image processing CGRA to a CGRA that's specialized for each of these individual applications, we see a corresponding decrease in both the PE and CGRA area and energy. And in the paper, we show more results for a wider variety of applications as well. So in conclusion, in this project, we developed APEX, which is a framework for automated design space exploration of CGRA PEs. It allows for the automated application domain-driven specialization of CGRAs. It includes automated hardware generation and compiler generation, and generates specialized CGRAs that have up to 39% less area and up to 59% less energy compared to a general purpose CGRA. With that, thank you. I'd be happy to take any questions.